So we will continue with the session with Professor S.C. Arora. Yes, sir. Yes, Anulla ji. Yeah.
So, friends, we were talking about weak convergence and strong convergence in non-linear spaces. I told you that a sequence xn in a non-linear space converges to x weakly if f of xn converges to f of x for every functional f in the space x star, the first conjugate space of the space x. That is the set of all bounded linear functionals on the space x. X in that case is said to be the weak limit. Weak limit, as you know, is unique. I told you that. An xn converges to a sequence xn converges to x strongly if xn minus x norm tends to 0 as n tends to infinity. X is called strong limit. Strong limit is also unique. And if xn converges to x strongly, then xn converges to x weakly. And if xn converges to x strongly, xn converges to y weakly, then also x is equal to y, because if xn converges to x strongly, it will converge to x weakly also, and weak limit is unique. Strong limit, weak limit are unique. Surprisingly, strongly convergent sequences and weakly convergent sequences, they are both bounded. Strongly convergent sequences are obviously bounded. Well, simple fact, if xn converges to x strongly, suppose xn is strongly convergent, and if xn converges to x strongly, then xn minus x norm tends to 0 as n tends to infinity. Okay, so that means, say if epsilon is equal to 1, that means there exists some positive integer m such that xn minus x norm is less than 1 for all n greater than or equal to m. It means xn norm therefore is less than or equal to xn minus x norm plus x norm. That means xn norm is less than 1 plus x norm for all n greater than or equal to m. And if we choose k to be maximum of x1 norm, x2 norm, xm minus 1 norm, and xn norm for all n greater or equal to m, then xn norm would be less than or equal to k for all n. So every strongly convergent sequence is bounded, but weakly convergent sequence is also bounded, because that follows by uniform boundedness principle. You know, the uniform boundedness principle as stated, that you can see that if X is a Banach space, and if A and B is a sequence of bounded linear operators from X to a non-linear space Y, then suppose for each X, then if this is A and X norm, see this individual sequence A and X, this is bounded, then A and norm, this sequence is also bounded. This is actually, uniform boundedness principle. Now, if we come to see this weakly convergent sequence, if xn converges to x weakly, that means fxn converges to fx. That means f of xn therefore is bounded, because every convergent sequence of complex number is going to be a bounded sequence. F of xn, this is bounded. Apply uniform boundedness principle. You see, uh, we will immediately therefore getting that xn norm there bounded. So every weakly convergent sequence is bounded. Every strongly convergent sequence is bounded. Strong limit and weak limit, I told you, they are unique. If xn converges to x strongly, it converges to x weakly, and weak limit and strong limit, they become unique. Every strongly convergent sequence is bounded, and every strongly convergent sequence is also bounded, and every weakly convergent sequence is bounded. Strong limit, weak limit, unique, all these things. Then um, we come to, you see, that if we consider, the question arises that if we have, say, if we consider finite dimensional nonlinear space, if we consider finite dimensional nonlinear space, weak convergence and strong convergence, I told you that strong convergence implied weak convergence, but converse is not true. But in case of finite dimensional spaces, weak and strong convergences become identical. Become identical means that every weakly convergent sequence is also strongly convergent. This follows immediately because taking, say, uh, taking say basis, say E1, E2, En of a finite dimensional nonlinear space is so, then you see each xn can be written as linear combination of say alpha 1 xn is alpha n1 E1 plus alpha n2 E2 plus alpha nk say ek of ek. Then there, by Hahn-Banach theorem, there always exists a functional which takes every, say, E1, E2, En, and say, for example, if you take E1 and E2, En, see there exists always a boundary linear function which will take E2 to En to 0 and takes E1 to 1. If that happens, that means we will get a sequence of complex number which is would be the sequence of coefficients of these xn, and they will converge. Taking the limit, taking the limit of all these and taking the maximum of these, then we will finally get xn will converge to x. Suppose if xn converges to x weakly, x is of the form alpha 1 E1, alpha 2 E2, alpha n En, and xn is alpha n1. Alpha n1 would convert to alpha 1, alpha n2 its sequence would convert to alpha 2, and take the maximum of these n's, we will get xn minus x norm. So every weakly convergent sequence is going to be strongly convergent. Strongly convergent already implied weak convergence, and weak convergence and strong convergence, they become identical in case of finite dimensional nonlinear space. So, question therefore arises that suppose there is a nonlinear space, and where in that nonlinear space, weak convergence and strong convergence are identical. Will we get that this space is finite dimensional? The answer is definitely no. Because there are infinite dimensional nonlinear spaces where weak and strong convergences are identical. But still, the space is infinite dimensional. For example, the space L1. What is the space L1? This is the space of all sequences. It becomes L1 is a Banach space. Of course, it is not a Hilbert space correspondingly. Inner product is not corresponding. In the space L1, it is an infinite dimensional space where weak and strong convergence are identical, yet the space is infinite dimensional. Right? So, with this we we change the topic, and we now talk of the convergences in major spaces. Of course, the convergence in non-linear spaces does not end over here. We can talk of weak star convergence, and we may say many things more because the things which can be discussed, which can be talked about, that all these convergences, they lead to topology on the spaces. We can talk of weak topology, we can talk of course, strong topology, we can talk of weak star topology, etc. And much more discussion can be talked about, can be discussed in reference to convergences, convergent sequences. It's a vast topic leading to many more things. many more discussion. But in any case, because in this we are to talk of limited things only, and we uh, take our limit only up to this, and we go to major spaces. Come to convergence in major spaces, which we can discuss. What is a major space? Of course, major space in non-empty set X and A sigma algebra of subsets of the set X. What is the sigma algebra? Sigma algebra is the collection of subsets of the set X, of course, containing the empty set and the closed under arbitrary union and also complementation. You know, uh, if X belongs to this, so if A belongs to the collection A, then X minus A also belongs to its complementation, and union A and going from 1 to infinity also belongs to the A for if each A n belongs to the collection A. Mu measure. What is a measure? It is a non-negative extended set valued function defined for each A belonging to A, such that mu of empty set is equal to 0, and mu is countably additive, in the sense that mu of union An is equal to sigma of mu of An if An intersection Am is equal to empty for n not equal to m. This is called the measure. And this triad X A mu is called a major space. In the major space, we can discuss the following type of convergences. Of course, we can discuss many more things, but in reference to convergences, we can talk of uniform convergence, number one. Number two, uniform convergence almost everywhere. Number three, almost uniform convergence. Number four, convergence almost everywhere. And number five, convergence in measure. At the moment, what I have chosen to discuss is the following. The implications and the relation, these are all outfits of firstly uniform convergence. I'll give you proper definitions. I've shown that first implies 2, 2 implies 3, 2 implies 3, and 3 implies, first implies 2, converse not true. 2 implies 3, converse not true. 3 implies 4, converse not true. 3 implies 5th, converse not true. And 4th does not imply 5, and 5 does not imply 4. This is what I'll prove by giving you examples, counter examples, etc., etc. Firstly, let us address to the definitions. Definitions, firstly. That is what I'll give you interesting examples, where the converse implications are not true, etc., etc. But this is what my target at the moment is, that I'll talk about. These are outfits of uniform convergence in major spaces. Firstly, definition. Definition of what? Uniform convergence, firstly. A sequence Fn of measurable functions on the major space A mu. This triad X, non-empty set, A, sigma algebra, mu, set valued function defined for each A belonging to A, the non-negative extended real valued function. A sequence Fn of measurable functions on the space X A mu is said to converge uniformly to a measurable function f if for each epsilon greater than 0, there exists M such that f and x minus fx modulus, because this will now become a real number, f and x minus fx modulus is less than epsilon for all n greater than or equal to m and for every x belonging to x. Next is, you know, a sequence fn of measurable functions. Measurable, I hope everybody understand what is a measurable function. You see, and if the set of all those x for each alpha such that fx is greater than alpha, this is a measurable set. What is a measurable set? A set is said to be measurable if it belongs to A. You know. So, a sequence Fn of measurable functions on the measure space X a mu is said to be uniformly convergent almost everywhere. Uniformly convergent almost everywhere, I am defining at the moment, is a sequence Fn of measurable functions on this measure space X a mu is said to be uniformly convergent almost everywhere to a measurable function f if there exists a measurable subset A of x with mu of A equal to 0 and Fn converges to F uniformly on its complement. Fn converges to F uniformly on x minus A. That is, for each epsilon greater than 0, there exists M such that Fn x minus Fx modulus is less than epsilon for all n greater than or equal to m and for every x belonging to x minus a. Of course, mu of a is equal to 0. If there exists a measurable subset A of x with mu a, in short, what does it mean? We say Fn converges to uniformly convergent almost everywhere if we take away a measurable subset of measure 0 and on the complement it is uniformly convergent. Uniformly convergent I have already defined on the whole set X. The next, a sequence Fn of measurable functions is said to converge almost uniformly convergent on the measure space X a mu to a almost uniformly convergent. Uh, Measurable function f. If for each epsilon greater than 0, there exists a measurable subset A of x with mu of A less than epsilon such that Fn converges to F uniformly on x minus A. This is what? This is almost uniformly convergent. Next, a sequence Fn of measurable functions converges everywhere. Almost everywhere means you take away if it is so, on the complement of, you see, a measurable subset of measure 0. A sequence Fn of measurable functions converges almost everywhere. This is pointwise. Converges almost everywhere to a measurable function f on the measure space x mu. If f and x sequence, this is sequence, converges to fx for every x belonging to capital X, except on a set of measure 0. That is, there exists a measurable subset A of x that mu of A is equal to 0 and f and x converges to fx on x minus A. Then, next definition. A sequence Fn of measurable functions is said to converge in measure to a measurable function f on the measure space x a mu if for every epsilon greater than 0, limit of this set, this is set, the set of real numbers now, all those mu of x such that Fn x minus fx mod is greater than epsilon. Limit of this is now mu of this, it makes it a real number. So limit of mu of this and infinity is equal to 0. That is, for every epsilon greater than, there exists a positive integer m such that for all n greater than or equal to m, mu of all those x such that Fn x minus fx mod is greater than epsilon is less than epsilon. Equivalently, see, these two mu's are there. One can see that this is the equivalent to that for every epsilon greater than 0 and delta greater than 0, there exists a positive integer m such that for all n greater than or equal to m, mu of all those x such that fn x minus fx mod greater than delta is less than epsilon. Right. So these definitions, as I mentioned earlier, it is interesting to see that in general the following relations exist in these various type of convergences. Uniform convergence implies uniform convergence almost everywhere, but is not implied by it. And uniform convergence almost everywhere implies almost uniform convergence, and almost uniform and but is not implied by this. And almost uniform convergence implies convergence almost everywhere, and also almost uniform convergence implies convergence in measure, but convergence almost everywhere and convergence in measure, they are not related. This is interesting to see that these are the implications. We will prove them one by one. Let us see. We prove these relations as follows. Let's see the first one. Uniform convergence implies uniform convergence almost everywhere. When see uniform convergence is there throughout on the whole space X, then whether you take take away any set or you do not take, you take the set empty, this is zero, fine. That follows that uniform. It trivial. One implies two trivial. Uniform convergence implies uniform convergence almost everywhere. But interesting part is to see that the converse is not true. Converse is not true. For example, if I take x to be the interval 0, 1. Now, these are the things to be seen. And mu to be Lebesgue measure. Lebesgue measure, I hope you understand. The set is said to be Lebesgue measurable. Set uh, E is A is said to be measurable if mu of A is equal to mu of A intersection E plus mu of A intersection E complement. For every E belonging to the algebra A to be Lebesgue measurable set. Let Fn, let Rn be the set of all rationals. You know, the set of all rationals is a countable set in the interval 0, 1. And the complement of it is set of all rational, and they being countable, so therefore they can be put in the form of the sequence Rn. Define Fn as follows. Fn x is equal to 1 if x is rational and x belongs to R1 or R2 Rn. And 0 if x is rational and but x is not equal to, Ri, I going from and see the complement of these rationals, and see, I can say Fn x is equal to 1 if x belongs to R1 or to Rn and 0 otherwise, defined on the interval 0, 1. See, Fn is defined like that. And define Fx is equal to 0 for each x belonging to the interval 0, 1. Then for each n and f, each n and f are, you can see they are measurable functions. What is a measurable function? I told you that. You see, and A is the set of all rationals in 0, 1. A is the set of all rationals in 0, 1. Because it is a countable set, therefore mu of A is equal to 0. Okay. And Fn converges to F uniformly on 0, 1, the complement of this set A. However, Fn does not converge uniformly to F on the whole interval 0, 1, because limit of Fn x and tending to infinity is equal to 1 if x is rational and 0 if x is irrational. Right? Why this is so? because if x is rational, then x would be equal to, you see, x would be equal to some Ri, and therefore f and x after that Ri, see Ri, it would be equal to 1. Therefore, limit would be 1. Therefore, limit of f and x as n tends to infinity would be equal to 1 if x is rational for every rational f. By the way, this also gives you, this is also serves an example of that function such that the pointwise limit of a sequence of Riemann integrable functions may not be Riemann integrable, because you can see that each fn is Riemann integrable because it is discontinuous only, each fn is discontinuous only at finite number of points, and therefore each fn is integrable on the interval 0 1, and f is not Riemann integrable because fx is equal to 1 if x is rational and 0 otherwise. This also serves the example of, a beautiful example of sequence of Riemann integrable functions not converging to pointwise to a Riemann integrable function. Where here you know that uniform limit of a sequence of Riemann integrable functions is always Riemann integrable. This also gives you an example of this type. Then, second example. Second example is, uniform convergence almost everywhere implies almost uniform convergence. Let us recall what is uniform convergence almost everywhere. Uniform convergence almost everywhere. That means, it, leaving a set of measure 0, it is uniformly convergent. And almost uniform convergence means that for each epsilon greater than epsilon fn converges to f uniformly on the rest of it. This is this therefore follows by definition that uniform, because there mu of a is equal to 0 for each epsilon greater than 0. Therefore, mu of a would be less than epsilon always because it is already equal to 0, and therefore second implies third is immediate. Let us observe what is the reverse implication, that almost uniform convergence may not imply uniform convergence almost everywhere. We again take, let x be equal to the interval 0 1, and mu once again Lebesgue measure. By the way, it's a finite measure because since it is Lebesgue measure, therefore mu of whole of x would be equal to the length of the interval. A is the, and if we take A to be the set all Lebesgue measurable sets, those subsets of the set X which are Lebesgue measurable, define a sequence fn converging to f of functions on 0 1 as follows. Fn x is equal to x raised to power n, x greater than or equal to 0, less than or equal to 1. And fx is equal to 0 for all x greater than or equal to 0, less than or equal to 1. Take the limit of these fn x for each point twice. No, it would be for x strictly greater than or equal to 0 and strictly less than 1, it would be 0, and it would be 1 on the on x x is equal to 1. So this means, on the whole interval 0 1, leaving the point 1, you see fn x is converging to fx, and various on the we can prove. Here is the proof. Let epsilon greater than 0 be any real number, and let a be equal to open to the side of epsilon on the side of 1 minus epsilon by 2. 1 minus epsilon by 2 to 1. What is mu of a? Length of the interval. This is epsilon by 2, and that is less than epsilon. And fn converges to f uniformly on 0 to 1 minus epsilon. That means we are able to find out a subset A for each epsilon greater than 0. We are able to find out a subset A, we find the subset of A such that mu of A is less than epsilon. And Fn does not converge to F on the whole of it. You converge to F uniform convergence almost everywhere. Let it possible this be so. Take epsilon equal to 1 by 2. Then as there exists some A such that Fn converges to F uniformly to 0, 1 to A with mu of A is equal to 0. That is, there exists M such that X and mod is less than 1 by 2 for all n greater or equal to M. And for every X belonging to 0, 1 minus A. Then X and mod is less than 1 by 2 for all X belonging to 0, 1 minus A with mu of A is equal to 0. Limit of X raised to power M X tending to 1 is equal to 1 because it's a continuous function. Therefore, we can choose Y such that Y greater or equal to 0 and less than 1 such that Y of M greater than 1 by 2. Now, Ym cannot be a subset of A since mu of A is equal to 0. Therefore, any X greater or equal to Y satisfies Xm is greater than 1 by 2. So, this follows that third may not imply 2, right? Okay. But third implies fourth. Almost uniform convergence implies convergence almost everywhere. Third implies fourth. Almost uniform convergence implies convergence almost everywhere. Almost uniform convergence, meaning thereby that for each epsilon greater than 0, we can take away a subset A such that mu of A is less than epsilon and Fn converges to F uniformly on its complement. This is so let an Fn converge. Well, this requires little proof and little observation, and that is how almost uniform convergence implies convergence everywhere. Because for every epsilon, we would be finding out a subset, taking away a subset A, and therefore for each n, uh, let Fn converging to F almost uniform in a major space XMU. Therefore, by definition, for each positive integer m, there exists a measurable subset am of x such that mu of am is greater than is less than 1 by m, and Fn converges F uniformly on x minus am. Fine. This means that if we take the intersection of all these am, what would be mu of that? That would be 0. Let A be equal to intersection am, m going from 1 to infinity. So what is mu of A therefore? Mu of A would be less than mu of am, that is less than 1 by m for all m. Therefore, mu of A would be equal to 0. Mu of A is equal to 0. And on its complement, x minus A is x minus by De Morgan law, it is union of x minus am, m going from 1 to infinity. And we claim that Fn converges uniformly on x minus A. So let x belong to x minus A. Therefore, there exists m such that x belongs to x minus am. Obviously, when x belongs to x minus A, it is union of x minus am, so there exists. And then Fn converges uniformly on x minus am, and hence pointwise on x minus am. That is, Fnx converges to Fx pointwise on x minus a. Therefore, Fn converges to F. The convergence almost everywhere. Convergence. Third implies fourth. Convergent almost everywhere. Right. However, converse is not true. That is, convergence almost everywhere may not imply almost uniform convergence. Let's see this example. Let x be equal to R, the set of real numbers. Mu Lebesgue measure, the usual measures in Lebesgue measure space. A Lebesgue measurable sets. Define a sequence Fn as follows. Fn x is equal to x by n going from 1 to 3 and so on for every year. So what is the pointwise limit? Pointwise limit is obviously 0. Define fx is equal to 0. You see, when for each fixed x, when n tends to infinity, it tends to 0. So Fn converges to f, then Fnx converges to 0 as n tends to infinity for every x belonging to f, and hence Fn converges to f, almost everywhere. And therefore, however, Fn does not converge almost uniformly convergent to f. For suppose we take epsilon equal to 1, then let there exists a subset A of R with mu of A less than 1, and Fn converges to f uniformly on R minus A. Hence, for epsilon equal to 1 by 2, there exists therefore m such that x by n, this is how it has been defined, x by n is less than half for all x belonging to R minus A, and for every n greater than or equal to m. But however, if we take n equal to m, we can choose always that we can choose x greater than or equal to m and x belongs to R minus A, such that x by n becomes greater than or equal to half 1, which is because x can be chosen to be arbitrarily large, very large, belonging to the set of real numbers. So therefore, x by n will always become, x by m will always become greater than or equal to 1. Therefore, Fn does not almost uniformly converge to f. Next, our next implication. Third implies fourth. What is that? Almost uniform convergence implies convergence in measure. Let us recall what is convergence in measure once again. We say that a sequence Fn of measurable function is said to converge in measure to a measurable function f on the measure space xmu if for every epsilon greater than 0, limit of this sequence of real numbers, limit of mu of all those x such that fn x minus fx mod is greater than epsilon, and mu of that would become therefore a sequence of real numbers, limit of this n tending to infinity is equal to 0. That is, for every epsilon greater than 0, there exists a positive integer m such that for all n greater than or equal to m, mu of all those x such that fn x minus fx mod is greater than epsilon, less than epsilon. And equivalently, in terms of epsilon and delta, I told you the definition. And we are now trying to prove that almost uniform convergence. Almost uniform convergence means that for every epsilon greater than 0, we can take away a subset A of measure less than epsilon, such that on the complement of it is uniformly convergent. So let us now prove that how this third implies fourth, and of course third and fourth, they are not and fourth does not imply third. Let Fn converge to F almost uniformly converge in the measure space XMU. Suppose this is, then let it possible Fn doesn't converge in measure to function F. That means there exists a pair epsilon greater than 0 and delta greater than 0 and a subsequence Fn k such that for each k going from 1 to so on, mu of all those x, all those x such that f and k x minus fx mod greater than epsilon is greater than or equal to delta. Reverse implication of that, right? Now for this delta greater than 0, there exists a measurable subset A of X such that mu of A is less than delta because it is almost uniformly convergent, So therefore, using that almost uniformly convergent, for this delta greater than 0, there exists a measurable subset A of capital X such that mu of A is less than delta and Fn converges uniformly on X minus A. Hence, for this epsilon greater than 0, when Fn converges to F uniformly on X minus A, therefore, for this epsilon greater than 0, there exists M such that Fn X minus Fx mod is less than or equal to epsilon for all n greater than or equal to M and for every X greater than or equal to A. This implies that for every n greater than or equal to M, all those X such that Fn X minus Fx mod greater than epsilon should be contained in A. And this implies, therefore, that mu of all those x such that Fn x minus Fx mod greater than epsilon is less than or equal to mu of A, and that is less than delta. Choose k to be choose k such that nk becomes greater than m. Therefore, this is possible because it's a subsequence leading to infinite. Therefore, mu of all x such that Fn kx minus Fx mod greater than epsilon, this is less than delta because this would follow from there a contradiction. Therefore, Fn converges to F in measure. Right? Converse is not true, surprisingly. Let x be equal to 0, 1, interval 0, 1, and mu once again Lebesgue method. And A to be Lebesgue measurable set, A to be the class of all Lebesgue measurable set. And let n denote the set of natural numbers. And we partition the set of natural numbers in this way. N to be, which is the set 1, 2, 3, 4. Take this to be singleton 1, union 2, 3, then 4, 5, 6, 7, then next 8, 8 to 15, and so on. Now define a sequence Fn of functions as follows. F1x is equal to 1, firstly. Then F2x is equal to 1 if x belongs to 0, 2 half, and 0 otherwise. And for 4, 5, 6, 7, we write F, and of course F3x is equal to 1 if x belongs to half. So we have defined F1, F2, F3, and next 4, they are defined by taking partitioning the interval 0, 1 into 4 parts, 0, 1, 0, 1 by 4, 1 by 4 to 1 by 2, 1 by 2 to 3 by 4, and 3 by 4 to 1. And define F4x to be equal to 1 on the first interval, 0 otherwise, F5x to be equal to 1 on the second interval, second subinterval, half 1 by 4 to half, 0 otherwise, and like that. Like that, we can define F5x, F6x, and so on. In general, we observe that in general, if n is of the form k plus 2 raised to power m, k greater than or equal to 0, less than 2m, then Fn x is equal to 1 if x belongs to k by 2m to k plus 1 by 2m and 0 otherwise, and so on. You can see, if you see the pattern of the sequence F1x, F2, F3, then F4, F5, F6, F7, and so on. It follows this pattern that if n is written as the form broken up into the pairs of powers of 2, like that, and if k n is of the form k plus 2m, k greater than or equal to 0 and less than 2m, then Fn x is equal to 1 if x belongs to this and 0 otherwise. Then mu of all those x such that Fn x, we observe mu of all those x such that Fn x, mu would be the length of that interval. Fn x greater than epsilon would be equal to 1 by 2m because n is of the form k plus 2m, the way it has been broken up. When n is of the form k plus 2m and 2m is less than 2m plus 1. Cool. n is when n is less than this, and 1 by n. Therefore, 1 by m becomes greater than 1 by 2m plus 1, and 2 by n therefore becomes greater than 1 by 2m. Mu of all those x such that f and x is greater than epsilon would be less than 2m, and therefore limit of this would be equal to 0. Thus, fn converges to f in measure, where fx is equal to 0 for all x. But for any x, there exists large value of n uh, such that f and x is equal to 1. Therefore, f and x does not converge to fx for any x, because fx is going to be equal to 0. And so fn does not converge to f almost every uniformly. So fifth does not imply 4. The above example shows that fn converges to f in measure, and fn x does not converge to fx for any x. So it is not convergent almost everywhere. Fourth does not imply 5. Why? Because again, if we take let x to be equal to r and mu to be Lebesgue measure and a to be Lebesgue measurable set, if we take a to be Lebesgue measurable set, if we define a sequence f and converges to f as f and x is equal to x by n going from 1 to so on, and define fx is equal to 0, then fx then fn converges to f almost everywhere. In fact, it is everywhere convergent, because when n tends to infinity, limit of f and x is equal to 0. And so, but for any epsilon greater than 0, mu of all those x such that f and x minus fx mod would be greater than epsilon. Here fx is 0 and f and x is x by n, and this is going to be equal to, you see, infinite for every n. Therefore, fn does not converge to f almost everywhere. And this finishes the whole thing. And I may invite now any doubt, problems, etc. Any questions? If there are certain references, you know, the, I made a collection from the history of history to mathematics education, and a book by Ball, a short account of the history of mathematics, printed 1960, and then these are books for measure and integration, T.T. Barrett's book, and R.G. Bartle's real analysis book, and again Bayer's mathematics, and Kajori's book, Evaluation of Criteria of Convergence, Bulletin of New York. This is the research paper, 1892, and these are History of Mathematics. This is the book written by Kajori, History of Mathematics, second edition, 1990, and named Divergent Series, 1923, and book by Divan, where he made the mistake, Cauchy's book, Course the Analysis, 1821 book. Driver analysis tools with application. Now, history of mathematics. Of course, made a search for my own topic, convergence, from all these history books of history written on mathematics. Any question? I invite any doubt, any question, if there are any. See, what I want to say is mathematics is such a large topic of such magnitude that there is no end to speaking about anything. You see, I remember, once I was delivering a lecture at Yamuna Nagar, Haryana, the lady who was trying to introduce me said, while in my introduction, she talked about mathematics and said, पानी रे पानी तेरा रंग कैसा, जिसमें मिला दो लगे उस जैसा. And then she started explaining that mathematics is such a topic, mathematics for commerce, mathematics for economics, mathematics for medical line, mathematics for biology, mathematics for physics, mathematics for chemistry, mathematics for economics, mathematics for commerce, etc., etc., etc. So she said that, you see, mathematics can be compared with water. That whichever pot it is poured in, it takes that shape. While delivering lecture, while beginning with my lecture, that I said that I would like to give comment over whatever that I think I remember still. Her name was Rachna Agarwal. That whatever Dr. Rachna Agarwal has said regarding mathematics and analogy with water, I would say I am also remembered of some lines from a song. I said that ओहरे ताल मिले नदी के जल में, नदी मिले सागर में, सागर मिले कौन से जल में कोई जाने ना. Meaning thereby, the analogy, what she has said is fine. But my analogy takes this situation a little further. That mathematics is just like water. From where it has come, where it would go, nobody knows. It is such an infinite thing, going from minus infinity to plus infinity and covers the whole world. Nobody knows. If you try to trace the history, it comes right from the birth of mankind. Where it would go, nobody knows. Where it would end, nobody knows. Takes that analogy of Dr. Rachna Agarwal little further. This is what I want to say. That you see, you are lucky that you are in the subject of mathematics. It begins with the beginning of civilization. And to what extent it would get developed, nobody knows. Which miracles it is going to create, nobody knows. Which advances it would go to, nobody knows. Where it has come from, how mathematics came suddenly, and where it would go, nobody knows. You are lucky to be in this particular subject, which is applied everywhere, omnipresent, equivalent almost to God. You see, it is mathematics. Right. Okay. Thank you. Thank you very much. Anything else, would like to say? I would welcome.
Yeah, any questions if you have, you can ask. Yeah. Yeah, Anumala ji. Yeah, please. Yeah.
I thank Professor S.C. Arora ji for his elaborately explaining about convergence from the ancient times to present age and the convergence in measured spaces, leaving no gaps of doubts and confusion, sir. I think every participant is benefited by his talk. Also, his anxiety to present the talk at this age is highly appreciable, and we, the young generation, has to learn more from him. Sir, is an example for age is not a bound for learning and teaching. Once again, I thank you, sir, for your elaborate presentation. Thank you very much, sir.
Thank you.
Sir, among